All right, so let's see how the idea from that last problem works in general. If we want to find eigenvectors, and we know what lambda is, we want to find vectors x that make this equation and the definition true. And to find what x makes it work, we could just subtract the lambda from both sides. And then let's notice that lambda x is really equal to lambda I times x. So yeah, you can see why if you multiply this lambda times I diagonal matrix times x, you're just going to get the same thing as lambda times x. So those are the same, and then we have a distributive rule you can use to factor out the x from that. And so, yeah, these equations are equivalent. And this first equation is just the original definition of what makes eigenvectors and eigenvalues. And so we have this alternative definition that the original definition is equivalent to this equation here. And of course, we still have that eigenvectors are only allowed to be non-zero vectors. In other words, given any particular eigenvalue lambda of A, the set of eigenvectors corresponding with lambda is the null space of A minus lambda I, because the null space is defined to be the set of vectors x that satisfy this equation, except for, of course, 0. The 0 vector is in the null space, but isn't an eigenvector. So anyways, the vector space null A minus lambda I is called the eigenspace of A corresponding with lambda. So yeah, given an eigenvalue, we just need to solve this homogeneous equation, describe the null space of A minus lambda I. But if you don't know eigenvalues, how do you find them? Well, let's see. First, let's fill in the blanks here using the invertible matrix theorem. And if you want to pause this, it's a good idea to try to remind yourself of this on your own. But anyways, I'll show you the answer now. The invertible matrix theorem says that A is invertible if and only if the null space of A is equal to 0. But that means that A is not invertible if and only if the null space of A is not equal to 0. And likewise, A is not invertible if and only if the determinant of A is equal to 0. Okay, so if we apply this fact here, the fact that these two things are equivalent to A minus lambda I now. The null space of A minus lambda I is not just the 0 vector, meaning there's non-trivial solutions to A minus lambda I equals 0. That's true if and only if the determinant of A minus lambda I is 0. And the second one here is the definition of eigenvectors and eigenvalues, that if there does exist a non-trivial solution of this equation, then lambda is an eigenvalue. So this shows that solutions, values of lambda, that are solutions of the characteristic equation, which is this, the determinant of the matrix A minus lambda I is equal to 0. Solutions of that are eigenvalues of A. So this is going to be an equation where the only variable is lambda, because hopefully you're given a particular matrix A, and when you do this determinant, you're going to get a regular old scalar equation, what turns out to always be a polynomial, where lambda is the variable, and any lambda that makes that determinant equal to 0 means you're making A minus lambda I a non-invertible matrix, which means the null space of A minus lambda I is not just the 0 vector, which means there exists an eigenvector in this null space that corresponds with your eigenvalue lambda. So let's see how this works with an example. Let's find the eigenstuff of this stochastic matrix. This is the kind of thing where you might want to get like a sequence of powers of this that we looked at in 4.1 to describe like two groups of people where like 90% of one group is like staying in group 1 and the other 10% of one group is moving to group 2, that kind of thing. Anyways, let's see how it works. So the characteristic equation is the determinant of A minus lambda I should be equal to the number 0, and actually subtracting this gives you 0.9 minus lambda, 0.1 minus 0, 0.05 minus 0, and 0.95 minus lambda. And this is just a 2 by 2 matrix, so its determinant is going to be like AD minus BC, or in other words, 0.9 minus lambda times 0.95 minus lambda. And we might need a calculator for this. What we're going to get from this is lambda squared minus 0.9 lambda minus 0.95 lambda comes out to be minus 1.85 lambda, and then the 0.9 times 0.95 minus 1 times 0.05 is 0.85. All right, so let's see how to solve this. You could use the quadratic formula here, of course, but there's an easier way. Can you think of how to factor this? Are there two numbers here and here that when you multiply them, you get 0.85, and when you add them, you get negative 1.85? Just the old factoring rules, but having decimals makes it a little confusing. Turns out you can. That should just be minus 1 and minus 0.85, because negative 1 times negative 0.85 is positive 0.85, and minus 1 minus 0.85 adds up to negative 1.85, so it works. And that means we get lambda equals 1, and lambda 2 is 0.85. So these two numbers will make it so A minus lambda times I is a non-invertible matrix, which means there exists an eigenvector x that makes that true. So let's start by finding an eigenvector x that corresponds with lambda 1 equals 1. So to make x an eigenvector that corresponds with lambda 1, we need to solve this homogeneous equation. A minus 1i is going to be, well, 0.9 minus 1 here will be negative 0.1. 0.95 minus 1 here will be negative 0.05. So here's the augmented matrix for that. Now you notice the rows are opposites of each other, so you can just add row 1 to row 2 to replace row 2 to get all zeros there. And maybe I can multiply row 1 by negative 10 to get 1, negative 0.50. So that means x1 minus 0.5 x2 equals 0 and 0 equals 0. That leads to solutions where x1 equals half of x2, and x2 is a free variable. In other words, the eigenspace corresponding with lambda 1 equals 1 is the span of 0.51. So just 0.51 is an eigenvector, or you could have 1, 2. There's an infinite number of eigenvectors corresponding with lambda 1 equals 1. Let's do the same thing with lambda 2 equals 0.85. Any x that satisfies this equation will be an eigenvector corresponding with lambda 2 equals 0.85. And doing 0.9 minus 0.85 and 0.95 minus 0.85 will give you the following. Again, just writing this as an augmented matrix, we can row reduce this to get 1, 1, 0, 0, or in other words, x1 plus x2 equals 0, and 0 equals 0. And again, solutions of this, x1, x2 vectors, solving for x1 in terms of x2 gives you x1 equals negative x2. x2 is just x2, so we can write this as x2 times negative 1, 1. So in other words, the set of eigenvectors that correspond with lambda equals 0.85 is the span of negative 1, 1. So that is an example of finding eigenvalues using the characteristic equation, and then once you know those eigenvalues, finding solutions of the corresponding homogeneous equations, which gives you eigenvectors. Let's do another example of this. So this is the stochastic matrix from the infectious disease example. Let's find the eigenvalues of it first using the characteristic equation. So we're doing the determinant of A minus lambda I, and the lambda I is just going to have a lambda times 1 in the main diagonal and zeros everywhere else. So A minus lambda I will be 0.92 minus lambda, and then everywhere off of the main diagonal is unchanged. So we get this situation. We want to make this equal to 0. Now, to calculate this determinant might be a little gnarly, but there's a little bit of a shortcut. We can use a cofactor expansion along the top row because we've got some nice zeros in there that make it easy to multiply by. So this is going to be 0.92 minus lambda times the determinant of what you have when you cross out that row and column. And then we're going to do that minus 0 times some other determinant plus 0 times some other determinant, but it doesn't matter what those are. And this determinant is just of a 2 by 2 matrix, so we can just calculate that by doing the AD minus BC thing, like so. And let's try to FOIL this out. At least in the inside part of this, we can simplify this part. So that's how that 2 by 2 determinant simplifies, and we can use the same trick here to factor that part as what we used in the previous example. We can write that as lambda minus 1 and lambda minus 0.59. And fortunately, this one worked out to be easy to factor. So we can see we have these 3 different solutions of this that make the different factors of this equal to 0. So one is going to be lambda 1 equals 1. Another one is lambda 2 equals 0.92. And a third is lambda 3 equals 0.59. So Now let's find an eigenvector corresponding with lambda 1 equals 1. We want to find a solution of a minus 1 I equals 0. So a minus 1 I is going to be 0.92 minus 1, which is negative 0.08. 0.6 minus 1 is negative 0.4. 0.99 minus 1 is negative 0.01. So what we want is a solution to this, and a little bit of row reduction will lead this to this result here, which says that an eigenvector corresponding with this, a solution of this homogeneous equation, is going to be x1 equals 0, x2 minus 0.025 x3 equals 0. That leads to the eigenvector being multiples of x3, the free variable, where x1 is just 0, x2 is 0.025 x3, and x3 is just x3. So if you want to get whole numbers here, you could say x3 is 40. Now, what does that have to do with the situation? Let's go back and look at 4.1 when we first did this. We found that as time goes on, as like the powers of n here get really big, well, the result gets closer and closer to being this vector. And this, it turns out, is a multiple of that 140 vector we were just looking at. If you do 24.4 times 40, you get that 976 here, basically. So how do we know that a to the power n is going to get closer and closer to a multiple of the eigenvector that we have? Well, the gist of the argument is this, that in the long run, as n gets really big, the Pn vector is, well, it's always a to the n times the initial state vector, P0. I hope it's not confusing that I have P representing the sequence of vectors, but also capital P has the eigenvectors in it using the diagonalization theorem. And I don't know what B2 and B3 are. We didn't find those, but we did find one eigenvector is 0, 1, 40 here. And the diagonal matrix raised to the power n, well, 0.92 to the power n, that's going to approach 0. 0.59 to the power n is also going to approach 0 the bigger n gets. So you end up just getting P inverse, whatever that is, times the initial state, times 1 in the first component of this, and then the B2 and the B3 are basically going to get multiplied by 0. So the limit as n approaches infinity of P to the n is just going to be like this, which is just going to be some multiple of this eigenvector. All right, so that is an example of why finding eigenvectors and eigenvalues can explain the long-term behavior of these difference equations. We'll look at some more examples and also prove this important theorem about eigenvectors and eigenvalues in the next one. See you then.